Hello, everyone, and welcome to today's webinar, Accelerate Takeoff for New Aircraft Development with Virtual Reality. My name's Maria Ma, Marketing Campaign Coordinator for Engineering.com, and we're joined by our speakers for today. Welcome, Eric Kom, Senior Product Marketing Manager for IC-IDO at ESI Group. Eric promotes democratization of engineering applications used to identify, evaluate, and resolve potential issues to assure the OEMs have best chance to deliver safe, productive, and sustainable products. Also welcome Meredith Wood, a highly skilled virtual reality engineer at ESI Group. Meredith is entrusted with leveraging the company's VR platform, IC-IDO, to enable organizations to extract maximum value from the technology and seamlessly incorporate VR into their day-to-day engineering activities. Now, before we get started, we'll first cover our housekeeping items. Today's webinar will be available for on-demand replay on engineering.com. For attending this full live session, you'll receive your PDH certificate within 48 hours. And if you have any questions, please submit directly in this webinar interface, and we'll try to address all questions during Q&A. And now, without further ado, I'll pass it over to our first speaker. Eric, over to you.
Thank you very much for that kind introduction, Maria. Our topic today is accelerating takeoff of new aircraft development. And in the description of the webinar, you probably read some things about virtual reality. And I don't really want to focus on virtual reality. What I instead want us to focus on is how the virtual reality technology is being leveraged by people working in aircraft and aviation product development to validate what we call human-centric processes. So we're going to spend some time defining what we mean by a human-centric process, and we'll try to differentiate that from any other uses of virtual reality or extended reality that you might hear about when it comes to leveraging VR or XR technology. So the role of VR and XR when it comes to aircraft development can be used for doing things like validating those decisions that you make before you try to certify an aircraft. You can use it for discovery of issues and documentation of issues. You can use it to design and deal with those design and process volatility issues. And you can also use it to evaluate, are the procedures for aircraft maintenance safe? And are the assembly processes and the assembly order that you've defined appropriate? All before investing in physical build or placing your industrial athletes at risk. Now, before we get going, I would like to launch a quick poll just to get a better understanding of the people who've registered for today's webinar. So Maria, if you can launch that first poll.
Thank you, Eric. Attendees, do you have methods to predict how people can perform assembly or maintenance processes in a repeatable, effective, and safe manner? Yes, no, or unsure? We'll give you a moment to respond. And here are the results. 44% selected no, 33% were unsure, and 22% selected yes. Thank you so much for letting us know. Eric, back to you.
Thank you. So when we talk about this idea of validating a human-centric process, or a better way to just say that besides human-centric, is any process or procedure that humans play an integral role in performing that process, and they have to interact with these new products or new aircraft in the context of performing some procedure or process with that new aircraft product. So for example, one of the things that commonly happens early on in product development, so on screen right now, I've illustrated a generic worldview of how products could be developed in the aviation or aircraft, aerospace industries. So early on in that digital design and product design process, we're probably doing digital reviews where we're joining each other on screen, maybe in a web meeting, kind of like we're doing today for the webinar, or maybe we're meeting in a conference room as those folks are illustrated in that on that slide. A little bit later on, as we move away from just having the digital designs and we start manifesting, we start actually creating and bringing into reality physical proofs of concept, physical prototypes of those products. Maybe when we're getting ready for flight certification, maybe when we're getting that flight ready prototype out for certification and commissioning of that future aircraft. And then we actually have a physical aircraft to examine, to discuss, and explore. Now, at that point is probably when we can focus on product engineering and product integration concerns, right? So if we're doing an engineering review, we're looking at things on screen, now is the time for us to recognize that something about the product geometry, something about that product engineering decision is inappropriate for packaging, for space claim, or for people to work in and around. Maybe we have to redesign the part to make it more serviceable, or maybe we want to redesign the part to make it more manufacturable, or just make it so it better integrates with the rest of the aircraft. But once we cross past that milestone of having that flight-ready aircraft and actually getting that certification rubber stamp, that green light from the authorities that we can certify that aircraft, we start going into production ramp up. And this is when we start building up our production environments. Maybe we start building that up off-site and we migrate the tools over from a vendor or supplier into our production facilities. Maybe we start doing that, building the production line in situ on site. But now when we're really building physical parts and physical prototypes and those pre-production flight-ready aircraft, now is a time when we actually learn a lot by how will people interact with that product. And maybe as we're doing that production ramp up, and maybe as we're trying to optimize that production environment, we make discoveries that tell us that earlier decision about that manufacturing process, that earlier decision about that assembly process or assembly tooling, maybe that wasn't such a good idea, and we want to go back to the drawing board and make new decisions about how we do assembly or how we do service. And then once we start getting those aircraft into production and we start seeing serial production and we have a fleet in service that's actually flying, that's when we start really learning the most about how people will perform those maintenance or service processes on that future aircraft. Or at this point, it's not a future aircraft anymore, it's a current day aircraft. And the risk that we run into is that every once in a while we'll run into something where we can't just make a new procedural change, we can't just make a new tooling or workspace change, but in fact, we want to go back and change something about that product design. The risk, though, is that if we find something that is completely unbuildable with that product geometry, with that product design, and we have to go back to the drawing board and change the shape, change the topology of that airframe, of that aircraft, we run into issues that we might actually reset the clock on that certification process. So we don't want to run into a late emergence or a late discovery of something to do with that product geometry or that design for serviceability or that design for manufacturability once we've already had a certified flight-ready aircraft. We hopefully discovered all of the issues we had with product integration and those design for whatever. We made all those design decisions before we went into certification. After we come out of certification, hopefully we're only focusing on those human interactions with the product in the context of the processes we're trying to define and validate. Now, this is a very major challenge when we think about bringing a new aircraft to market. On screen right now, if you take a look at that idea of the pyramid on the left-hand side, we're just showing an illustration of how many problems can we emerge and visualize and potentially evaluate and resolve for quality, cost, delivery, and safety of that aircraft design and the procedures that bring it to market. Now, chances are those of you who on that survey said yes, you know that you're already doing some of this. Chances are you're using some of your CAD design tools, you're using some digital mock-up or DMU tools, or you have some sort of process planning, human-based process planning tool that you're working on your desktop. And that helps us emerge and helps us recognize and potentially resolve quite a few problems that could emerge. Now, if we couple that with using computer-aided simulations of what you might think of as deterministic simulation to simulate and analyze how the aircraft is going to function and how the aircraft is going to be assembled, we can learn a lot and maybe we can solve some of those issues. maybe by building physical prototypes and getting more of our experts to apply their expertise and apply their experience to looking at that aircraft design and the processes that we're planning for it, maybe we're able to resolve even more issues. But there's always that tip of the pyramid there where we always still risk that there could be something we didn't see because we didn't know to go looking for it in that digital data. There was no checklist, there was no master plan that said to look for it. And when you think about how that can affect the issue resolution and how quickly we can resolve that in the engineering process, early on in the engineering process, we knew what kind of risks existed for the last time we built that aircraft. So maybe we engineer those out early on in the engineering and concept phase. When we start doing that physical certification, we start building up that first flight-ready aircraft, then humans start building up that first airframe. They start maintaining that first engine, and they start running into newly found risks, newly found issues, and hopefully we resolve those before we exit certification. Then when we stop messing with our product data, we've frozen that data, and we start doing some production ramp up, maybe we had some preconceived notion of what would be the production or process issues that we could run into as we ramp up production. And so we try to resolve those, we launch the product, and then once we're at full serial production, then we start having this fleet in service. And it's quite possible that we emerge a big pile, a mountain of unanticipated risk. And what we're proposing with this idea of using virtual reality to perform a virtual build or a virtual maintenance or a virtual service procedure on a future aircraft is that I can go into VR and I can perform that maintenance operation or that build operation. And I can do so without waiting for that physical aircraft. And that means early on in my process, I can now emerge many of those risks that would not have been observed until after serial production started in earnest. Maybe I can resolve those long before a physical aircraft is built, before I make any of that investment in time and space and money to build a physical aircraft. And hopefully I can resolve a mountain of these issues long before the process of serial production starts. That's that leftward shift of not just the engineering work, but we're shifting to the left the opportunity to discover these kinds of issues. And that's what we're talking about when we mention the phrase human-centric process validation. All of those procedures where a human being has to interact with that product in the context of performing assembly, in the context of doing maintenance, or just operating that aircraft, if we can emerge those kind of issues without the physical aircraft, we optimize our opportunities to design our way out of those issues before we actually put anybody at risk and risk any of our investment or our assets in engineering. So generally, when we talk about this idea of doing human-centric process validation and doing this virtual product integration, what we want to do is we want to do all of these product-based decisions as early as possible by creating for people an opportunity for them to validate their product integration decisions. They're designed for service or they're designed for manufacturability decisions as early as possible. And then after we go through and start stacking up the line and start preparing the tooling, preparing the workspace for doing this assembly and service work in the future, we want to make sure that those assembly and maintenance process plans are validated, that we know that they work, and that there shouldn't be any surprises when we start going into physical build and physical mock-up. We are no longer surprised and making new discoveries. These are things we've already observed and hopefully mitigated out of design. And that's what we mean when we use the phrase human-centric process validation. So human-centric processes, as we asked in that poll earlier, how do you validate that and do you have a method? What I was asking was, do you have in your engineering process a time and a milestone when you are validating that humans can perform that final assembly and final trim out or final construction of that aircraft. That we know that for the variant aircraft or for the installation of any third-party componentry or bespoke componentry that goes into a particular airline's airframe, that we know that that can be installed and maintained by the human operators. We want to know that all of those MRO operations or procedures, removal or replacement, can be performed. And decommissioning an aircraft, decommissioning a product is of course very important. And if you think about today with space travel and space exploration in the direction it's going, doing that recovery and refurbishment or remanufacture of those repeated use rocket boosters that people have been bringing out to space exploration. These are all opportunities for us to validate that people can do that work a little bit better. So what we're going to do is we're going to go ahead and take a moment to launch another poll before I hand it over to Meredith, who's going to give us a few more examples of these procedural checks.
Great. Thank you, Eric. Attendees, how do you evaluate packaging, accessibility, ergonomics, and other factors when planning assembly and service processes? During tooling or equipment buy-off at a supplier's site? During engineer milestone release or gate meetings? With physical prototypes or mock-ups and pilot builds? Continuously with virtual reality builds? Or you do not? We'll give you a moment to respond. And here are the results. 50% selected during engineering milestone release, tied with 20% each selected with physical prototypes or they do not, and 10% selected during tooling or equipment buy-off at supplier site. Thank you so much for participating, and now we'll hear from Meredith.
Awesome. Thank you, Eric. You gave a really good introduction to VR and what that might look like. My goal here is to kind of give context. Everyone wants to accomplish those things that you talked about, right? We want to identify our issues earlier. We want to understand, how our operators are going to interact with our parts. We want to save our time and our money, right? So what exactly does that look like? So I performed an engineering review, which is what you're going to see on your screen here with this video here. So I'm immersed in ICIDO here, and that's what you'll see in the top of your screen, the top right, is you'll see my view in ICIDO. This is my first person interaction. And then on the bottom there, you'll see the third person kind of external view there. So as you see in my view, I'm looking at a battery install. This is a sub-assembly where we're just kind of looking at what path this battery is going to take. So I can get a really good understanding once I'm immersed of how I'm going to interact with this part, where my hands might be. If I have any reachability concerns or visibility issues, I'm going to be able to identify that right away. As soon as I'm installing this battery into its location, I'm going to be able to tell, if there's any of those issues, right? So we're looking at the installation and removal of this battery. And you'll see in the bottom left of your screen that image looking at the swept volume, which is giving us the exact path that the part is taking. So I can record myself installing or removing this battery, and it's going to show me the exact path. So I can get a good idea just by picking up that part, putting it into its position. But the swept volume is really going to quantitatively show me exactly what that looks like. So you'll see some of those collision arrows appearing there. And that's ICIDO telling me that I have some sort of collision. My parts aren't allowed to pass through each other based on what I denoted the properties to be. So again, I'm getting a really realistic view of what this install might be. So looking at the back side of the station, we're going to look at what if I don't have rigid parts? I have something like a wire or a cable or something flexible. Well, ICIDO can look at that as well. We can, take a look at some of our cables there. You can see I'm kind of reaching into that compartment, trying to get a look at a few of those cables. And when I did this, I actually noticed it was really uncomfortable for me. I'm on the shorter side, and I still had to bend into that little small compartment. I had to tilt my head. You can kind of see my green avatar there kind of tilting a little bit. And I asked my counterpart, why don't you try this out? Why don't you test this operation? Can you complete it from the backside? And we're having a real design review here, right? Where I can ask for direct feedback right away. and kind of understand what our operators will be doing without having to build one part, right? You know, I'm just taking this straight from CAD, importing in, and getting an idea for what this build might look like. So again, I'm looking at kind of the wiring and the cabling, being able to validate those lengths. I can quickly change those in and out if I see that maybe I have some slack, or maybe a cable doesn't fit into the slot that it needs to. And then just by, you know, performing this operation, I get an idea for what the operators are doing. So again, you know, I can understand the posture that they might have to do to complete this task. And in this case, it wasn't the best. So again, I can, you know, give that feedback to my designers or whatever stakeholders I need to, and tell them that, you know, we're going to have to find another way to complete this operation, because we don't want to have, you know, our operators go through this task, you know, every single time. So, a different data set, we're looking at maintenance operations. We're in this, the hood of this compartment, looking at this pump install. Again, you'll see my green avatar there. You'll see that the feet at the bottom there, I'm lifted, you know, 20 feet in the air, and my avatar feet are kind of leaning over. I'm really reaching as far as I can. Arms are extended to install this pump here. And I eventually get it into place, right? I can test all of my, you know, clasps there. I can reach the bottom ones, but the top ones are still a little bit more difficult. And again, I asked my colleague, hey, why don't you try this out? You know, this feels a little bit, you know, a bit of a reach for me. I'm leaning over the edge, and I'm already suspended 20 feet in the air, right? So maybe we need to figure out a different way for our operators to complete this. So again, we're able to validate this before we have a part created. I can test my tooling too. I can import, you know, this 90-degree drill here, test that I can see exactly where I need to hit my points. You know, again, I see my collision arrows noting that maybe that's a little bit tighter of a squeeze there, and I might not be able to drill down on that as I would need to. So we can test this out ourselves, right? As I'm immersed, I'm experiencing this exactly in a 1-to-1 scale. But we can also do this by using our Ramsys mannequin. So in NICIDO, we have our partnership with Human Solutions, where I can bring in a mannequin and I can understand and see exactly quantitatively where some of those areas of concern might be. So you'll see the shoulder kind of, you know, we've set these to our ergonomic standards, so I know exactly what is acceptable and not acceptable. So you'll see in the bottom left picture there, you'll see that, you know, maybe the back, you know, just as I suspected, right, as I was bending into that compartment to install this pump, I felt that my back was kind of extended a little bit. So I can validate this with my Ramsys mannequin and say, yeah, you know, this operation isn't going to be feasible because we have a lot of concerns on the back and the shoulders. And again, just validating my experience that I had in VR. So what about dynamic parts? You know, we've looked at some installation, some removal, some serviceability and tooling. But what about our dynamic tools, things like lift assist? You can see here we have our lift assist, installing our part into the eVTOL body in white there. And you'll see that we have all of our kinematics set up. So I can import my lift assist device in here. I can set up my kinematics and understand some of those clearances. You know, will this part be able to fit where it needs to? Is there any type of clearance issues we might have? Maybe we need to adjust the limitations of this assist device. And then as well as, and so when I was doing this operation, it felt pretty comfortable for me. Again, I'm a shorter person, but what about if my colleague who's 6 foot something, you know, puts on the headset, they can test this out too, and they can say, you know, maybe for someone your height, it might be acceptable, but for someone a little bit taller, maybe there's some visibility concerns or, you know, reachability, etc. So again, we can add our kinematics to this and test out our tooling. So going back to our first station there, we're going to talk a little bit more about process. So you'll see in the bottom right there, we have our ABOM tool there. So what I can do is I can record myself doing these operations. So I can hit record and I can complete my operations, you know, in the order that I think that they should be completed. And you'll see a little ghost version of this tool or these parts being assembled there. So what I can do is I can play that back and record myself and understand exactly how long it takes me to complete this operation. So maybe when we were designing this, we thought that an acceptable takt time might be 5 seconds or something. But once I record myself doing this operation and I look back, I can say, actually, it took me, 10 or 15 seconds. So that's something we need to consider when we're building our workstations here. And again, we can get a lot better idea of what this subassembly station might look like. Before we even have any parts available, we can look at, our current design. If the design changes, we can bring that in and validate that as well. But again, just another tool that we're able to use in ICIDO and kind of look at the sequence of our steps. We can also look at when we originally had this station, we thought that, we were going to install part A, B, and then C. But once I'm immersed and I'm kind of in the station and I'm put myself in the operator's shoes, I can say, actually it makes a little bit more sense to do B, C, A. And these are things that I can send back to our manufacturing team and tell them kind of what my experience was. So you've noticed that I've had a colleague with me in most of these engineering reviews. I've been working with my colleague, and we're doing our reviews, we're having some back and forth. But what might not have been obvious is that this colleague was across the country. We've been states away. So what we've done is we're able to jump into one session here and kind of, get each other's feedback right away. So we don't need to be in the same room. We don't need to be sharing headsets, switching those back and forth. We're able to jump into one session and collaborate immediately. And get each other's feedbacks. So again, we're looking at kind of the install process of some of these stations here, and collaborate with each other in real time and understand what some of those concerns might be. As well as if this operation did need 2 operators, we're able to understand what the operators are going to be looking at. So in this case, we're looking at some of that head clearance. So once I'm immersed in this space, I can tell that for me, my head was right next to some of that sharp metal, so that's going to be a concern. It was a really tight space, and we weren't able to maneuver as best as we can. So we were able to jump ahead in the future, transport to the future, and understand what this is going to look like for our operators. So talking again about ergonomics, one of the tools that we often use is RULA. A common ergonomic evaluation tool. RULA is Rapid Upper Limb Assessment. So we've looked at static poses of some of these, operations. So we have our mannequin that you see on the right, kind of in a static pose where we're able to validate that, and validate some of those concerns. But what about a more dynamic operation, which is exactly what you're seeing with the RULA animation on the left-hand side. We can record ourselves doing these operations and then play them back in real time and see exactly what our operators, where those areas of concern might be. So we don't need to, manually adjust this Ramses mannequin. We can just record ourselves doing the operation, and then again play that back and understand, where some of those concerns might potentially be. And then lastly, we are able to just become more familiar with our station here. Once I'm immersed in this this session, I can understand exactly where my part presentation is, how I'm going to turn to pick up a part. If I'm going to lean into that box there, I know for me, I had to kind of reach in there, and it wasn't the easiest operation. I could look at my visibility for that part presentation on the right-hand side and see, if I have to reach a little bit high or bend over. And again, just become a little bit more familiar with the process of this installation or build, and communicate that and some potential concerns that we might not have realized. Like Eric said, there's a lot of things that when we're jumping into a session that, okay, we have a concern about X, Y, and Z, but once I'm in that session, there's a lot that I might realize. So again, here we have, some install of a part on the bottom hand side of that engine, where once I'm, installing it, we thought it would be an easy install just to, reach under there, but really I need to bend down and make sure I'm driving that part in the correct area. So there's a lot that we can, learn from these sessions once we're in ICIDO and, testing out our existing data. Again, reiterating this, but without even having one physical prototype, we're able to kind of play with these mock-ups and understand some of our experiences. So I believe there should be another poll incoming, Maria.
Perfect. Thank you, Meredith. Attendees, how do you accommodate the reduction of access to physical prototypes and mock-ups in product development? Process validation begins at start of production, simulations reviewed on screen by stakeholders and experts, carpentry 3D printed and other mock-ups, gamification engineers build VR simulations, or you use digital mock-up and virtual reality solutions. We'll give you a moment to respond. All right, and here are the results. 45% selected process validation begins at startup production, and we have a three-way tie with 18% each selected simulations reviewed on screen, carpentry 3D printed and other mock-ups, and they use digital mock-up or VR solutions. Thank you so much for sharing. And now we'll go back to Eric.
Thank you very much. And thank you for all those examples that you walked us through, Meredith. And thank you for the poll feedback. It's amazing that, of those of you who are participating in today's webinar, the number of you who it looks like are in an opportunity-rich environment where there is opportunity for you to leverage VR or XR technology so that you don't have to wait until startup production to validate how humans are doing that job. And so we really see that there's an opportunity now for, without having to wait for physical startup production, without having to invest in building up a pre-production prototype that most likely will not be a sellable airframe, will not be a workable product that you can sell later on, because if you're using it to inform your engineering process, chances are you're going to make new decisions and invalidate whatever you were building. So there's a great opportunity here for us to leverage ICIDO and how we're using virtual reality to help you validate these decisions that you make. In fact, previously, before we were calling our product ICIDO, we called it a visual decision platform, that it was a platform for people to be able to make decisions based on visual and virtual reality so that they could experience the aircraft of tomorrow, today, and resolve those problems with product integration or design for service or maintenance long before anybody has to realize that physical aircraft. Now, another thing that's very important for us to discuss is that if we are in fact waiting until the start of production or until the realization of physical parts, there is a risk that we are also impacting our digital thread, and it creates gaps in the digital thread. And one of the most common gaps in the digital thread is this idea that once I have a physical aircraft and once I have people handling physical tooling in a physical production environment or maintenance environment, by that time, people stop updating the CAD data, and they don't always send those changes that they make to product geometry or to tooling geometry or the processes they've defined. They don't necessarily send those back. So what's being illustrated on screen right now is an example of our integration with PLM and PDM systems. So in this case, we're looking at PTC's Windchill product. And we've taken product and process information from the Windchill environment, and we fed that directly into ICIDO to instantiate an ICIDO virtual reality review. And then upon bringing that geometry and that process definition into the ICIDO working environment, now you can see another one of my colleagues performing that immersive tryout of the proposed process. So now we have a much closer, much narrowly defined digital thread that we can close by giving people an opportunity to experience, based only on digital data, only on the virtual design data, they're able to experience what it's like to do this assembly operation, to manage this assembly or construction environment, and walk around in it and feel for themselves, what is it like to pick up a part of that fuel tank, go pick up that tool, carry it over to do that next assembly operation. And we can validate all of this. If we had something that we observed that we didn't like about that process and we wanted to make a change, we could annotate and record that change and pass that back to the MPM, the manufacturing process management tool, so that that could be part of that digital trace, that digital thread. I think also just a moment ago in the video, you saw the footpath that I was traversing in that video. That I was walking back and forth across that floor, and I can get a really good idea of how many trips back and forth are people making as they're trying to do this job. Where is the free walking space need to be so that we can plan their work environment appropriately, so that we can have a better idea. Is it plausible? Is it practical to ask a human being to do this job in the future? And when the answer is no, that it's not practical, that it's not feasible, we have time enough, and we have not marched so far down towards start of production that we can't remake a new decision. And that's one of the key aspects of how we see people having an opportunity to close that gap in the digital thread. Now, one of the last things that I want to show everyone before we go into our Q&A period is to also double down on this idea of collaboration. The more that I can collaborate and the more opportunities I have to introduce the stakeholders, my peers, my production personnel, the people from our distributed chain of MRO operations throughout the world, if I can just teleport them, transport them into the future, and transport them all the way around the earth to another part of the earth where normally we would have to fly people to the site to experience this physical prototype. So if I was waiting for start of production at our pilot facility, or if I had our carpenters building physical mock-ups of this on the screen there, this proposed electric vertical takeoff and landing, or eVTOL aircraft, I don't have to wait until I built that thing up. I don't have to wait until it's real. And I don't have to put, if I did have a pre-production aircraft, if I did have a certification aircraft already, I'm not putting that asset at risk in order for me to do further validations. And we've seen this become critical for some of our customers who were recently, competing to see who would land a future aircraft program for their customers. And in that, they of course built a flying prototype. Of course they built a physical mock-up or mule that they were shipping around the world. But as they were having more of these commissioning meetings with their potential prospects, with their potential customers, they were able to walk their customers into that aircraft without having to ship anything. We would just put them into some virtual reality glasses, an HMD or head-mounted display, and they could experience for themselves what it's like to walk around that aircraft, to try to perform an oil change or a transmission change, or to load things into the cargo compartment, to climb into the passenger seat, to climb into the pilot seat. They were able to validate what it's like to really experience, to really participate in those processes with that future aircraft without having to slow down their engineering project in order to wait until they could validate those decisions with a physical build. And that's really where we see huge opportunities for people who are working in aviation innovation, in aerospace innovation, in space exploration. If we're trying to develop some new product that we hadn't ever built before, can we really afford to be late to market because we had to wait to find out these decisions? But also, we don't want to race to market without first validating these concerns. So this is really our best opportunity, the best of both worlds, if you will, to have our cake and eat it too. I can gain a significant amount of the experience that would normally only be gained, and only lessons that would only be learned when I had real people working with a real aircraft. I can learn those lessons now, today, on a purely digital, purely virtual aircraft. And then I can record that data. I can pass it back up to the PLM system. I can communicate to that, like that swept volume with real engineering data to people, and I didn't have to wait for it. So now I guess the only question is, what questions do all of you have for me and Meredith?
Awesome. Thank you, Eric. Thank you, Meredith. Here's your first question. On average, how long does it take to set up a VR simulation?
That's kind of a tricky question, because part of the VR simulation is the creation of that geometry data, but we're not going to include that. So we're going to assume that you already have the CAD data of either the product or that process. And really, in order to define that virtual reality experience, if you just want to see it in VR, as quickly as you can drag the data from your CAD interface into the ICIDU interface, and as quickly as that data can write over from one system to the other, you will be able to, in a matter of minutes, be able to see it in VR, walk around it in VR, and have some very basic interactions with it. If you wanted to do something a bit more detailed, like build up the physics of those rigid objects like that battery you saw us loading, maybe that would take about maybe 5 minutes to define that that battery is a solid rigid object, and that bulkhead that you saw me installing it in was a solid rigid object. Maybe that takes me 2 minutes. And then if we had to build up the interactions of that tool load, that assist mechanism, maybe that would take someone like Meredith probably about 5 or 10 minutes. It would take an amateur at driving the software like myself probably 30 minutes to a half hour. But either case, it's much, much faster than anything remotely similar to having a carpenter build that up, trying to make a mock-up out of Lego or 3D print. We can have that in a matter of minutes, that you're able to explore virtually and have that interaction with it in a matter of minutes. And many of our customers are able to run multiple VR reviews in a day. Hopefully that answers that question. If not, go ahead and ping us back.
Awesome. Thank you. Next question. Could you clarify how information flow is exchanged between digital twin, digital thread, VR, and the XR models?
Certainly. I mean, a lot of buzzwords in there, but first of all, if we think about the idea of just the digital thread. So for example, if you have your CAD geometry and you're using a PLM system, you just take that geometry out of your CAD system or out of your PLM system, and you bring that into ICIDU. Now, depending on how you bring that in, if you're doing it with our integration with PTC Windchill, that geometry can come in. We bring in the geometry, we bring in the process, and then any product process changes that I record, or if I flag something as requiring an engineering change, I can annotate that inside of my VR session, and then I can push that back into the PLM system. And that's probably the most cohesive way to do that. But this is not necessarily a digital, what you would think of as a digital twin. A lot of times when people talk about digital twinning, they're really thinking about a real-time live data connection. And that's not exactly what we're trying to achieve with ICIDU. We're trying to give you a virtual prototype experience that if you were to realize that part today by exactly the data you had in your CAD and your PLM system, we could bring that geometry in and we can give you that one-to-one, true-to-life kind of size and experience, and also some physics that you would be able to interact with. And then all of that stuff that we do in VR is recordable, and it's, when necessary, exportable, and I can hand that geometry back to my CAD operators. Hopefully, again, I hope I answered the question. So we're not doing any sort of real-time digital twinning here, right? A lot of people say they are, but we're not going to claim that right now. We are able to give you an opportunity to build up that virtual prototype and interact with it in the most rapid way possible, and with the least amount of having to code or having to learn how to drive some sort of video game building engine.
Understood. Thank you. Next question. How skilled does a user need to be to drive ICIDU?
Oh, that's a great question. I would say that the skills that are required to drive ICIDU are no different and no more challenging to learn than any of the stuff that you've been doing in your CAD workbench or in any of your computer-aided engineering and finite element. So what really we find is more integral to add into people's skill set is that we really have to take people out of being a digital modeling engineer or a virtual reality modeling engineer. And what we really want are people who understand the processes being modeled. So what's more necessary is that people have an inherent understanding of how assembly works. Because if I understand how assembly works, teaching you how to poke and click buttons in a user interface to simulate that assembly operation, that's pretty easy. What's a lot harder is taking somebody who's a computer science or computer modeling specialist and teach them things they didn't know about how airplanes are built or how airplanes are matured. So I would definitely say you don't need any specialized skill. You have to be mindful and care about what the outcomes or the outputs are from what we learn in VR.
Awesome, thank you. Can you have more than 2 people in collaboration sessions?
Absolutely. For example, we've done sessions before where I've had as many as 8 or 9 people simultaneously in a session. And I don't think I included that video in the webinar, but we have for other webinars and other events. And maybe you can find that on my YouTube channel, where we have maybe 6 or 7 engineers at Volvo who were all collaborating in the same virtual reality session. I would say, 10 is pretty reasonable, right? You can get 10. As soon as you have more than 10 people around, then it's just too many people inside of the same space to try to learn anything. But it is quite common for us to have a handful of people. One of the reasons why you see a lot of examples in our video sets of just 2 people collaborating is because we didn't draft enough people when we were recording those videos in order to have more people in. That was probably the bigger issue, was getting a hold of the humans themselves and not so much a technological challenge, but just getting people together to put on the headsets at the same time. That was a bigger challenge than the technological challenge of getting 5 to 10 people in a VR session at the same time.
Got it, thank you. Next question. Could this be tailored to work with the manufacturing of electronics?
This be tailored to the manufacturing of electronics? Well, I'm going to try to answer that fairly. Nothing that we've done inside of our software is necessarily tailoring it for one industry or the other. So absolutely, you could do it for aircraft, you could do it for electronics, you could do it for automobile, you could do it for marine architecture, things like that. But what I will say is that we really focus on applying ICIDO for things that are done at the human scale, but not necessarily the hand or handheld scale. I'm really thinking about manipulating things about like the size of that battery you saw us manipulating in that video when we were loading that battery into the back of that eVTOL. We're worried about the scale of how people can walk around and do these jobs. We're not so much concerned about can they pinch it between their fingers, can they hold it in their palm. We're really worried about can my hand fit in there with the thing that I'm holding. So that being said, we've done some very interesting stuff with people who were configuring avionics bays like you saw in that video that Meredith shared. On electronics at that scale, absolutely. If we're talking about building cell phones and building watches, you could do that in VR, but I would say personally, the things that we learn in that virtual environment are not quite as integral, and for us, not quite as necessary for us to apply our technology to solve as it is for the, those small, very super fine motor movements. So we're really thinking about, can I pick the thing up? Can I carry it a few steps over and put the thing in the product? So maybe we've done things with refrigerators and dishwashers, and some of our customers are making home goods, white goods. Maybe even some like servers and server racks we've done with people, but anything smaller than, I would say, anything smaller than a toaster, what we would do in ICI do is kind of overkill. It's a little bit more than is necessary to prove out that that thing works. Great question. Hard one.
Thank you. Next question. Which rendering engine did you use, Unity or Unreal, and how long to code?
Oh, we didn't use either of those. ICI do, we use our own rendering engine. So all of the videos that you see are being rendered in ICI do. And very importantly, we're taking the native CAD data and feeding that native CAD data. So if we're talking about PTC Creo CAD data, if we're talking about CATIA CAD data, we're talking about Siemens NX, we're taking SolidWorks, we're taking the CAD data and bringing it directly into our rendering framework. We're not rinsing it through any sort of geometry optimization tool, any sort of pre-decimation. So first off, we're not using anybody else's rendering framework. We're not relying on the game engines, and we're not getting beat up by people over some of those changes that have been happening in that Unreal pricing model that's happened recently. That's totally alien to us. We provide ICI do. It's its own rendering framework built into this high fidelity digital mock-up and extended reality tool that ICI do is. There was a second part of that question. Could you remind me of that, Maria?
And how long to code?
Oh, and there's no coding. Sorry, I should have remembered that. There was no coding. We're not asking anybody to learn how to code in the Unity framework. We're not asking anybody to learn how to code in the Unreal framework. You're not doing any code inside of ICI do. Now, our developers have built in a lot of that coding that would normally be required for defining physics, right? So if you were working, if any of you have experience and have built a proof of concept or a proof of value in some sort of game engine to do a virtual reality engineering build, you ended up having to define physics and physical interaction from the ground up by people writing code in those different coding engines, those gaming engines. And in fact, ICI do, the coding for that kind of behavior is built into the software because we're purpose built just to provide that environment for helping you validate your human-centric processes and performing those virtual reality product integration reviews. Awesome question, thank you.
Awesome, thank you. Next question, which headsets are you optimized to run on?
Okay, which headsets are we optimized to run on? One of the things that is a challenge for us, and sometimes people object to this, but you'll understand why in a little bit. Because we're working with the native CAD data, our rendering engine is super, super powerful, but it does require a powerful workstation. So one thing for sure, we are only going to be installing ICI do on either a laptop or a powerful workstation that has an NVIDIA GPU in it, right? So we have to have one of those professional GPUs provided by NVIDIA, and then we can run it. So that being said, it's a tethered headset, a headset that can plug into a wire. So we're talking about headsets like the Vario XR3. We're talking about headsets like the HTC Vive Pro, the Vive Pro wireless. I myself, I have an Oculus Rift S that I use. Works quite well on that. So let's see, the Oculus Rift S, the Vive,
HP, Reverb, Valve Index, yeah. I've got a whole list here, but we don't need to list them all. But yeah, I think you hit the most.
Right.
Vario, HTC, right. Oculus.
Perfect. And one caveat that I do have to warn you is that ICI do cannot be installed on a standalone headset. So if we're talking about the Meta Quest 2, the HTC Focus, right? Those types of headsets, they don't have that professional level GPU in them. They don't have enough RAM built in to be able to load a native CAD data set directly on there. So we do have to use some sort of attached to a workstation HMD. But pretty much any headset that works with Steam VR, chances are it'll work, but I won't necessarily say that we're optimized to them or what I would call fully supporting them or able to answer support questions.
Understood. Thank you. And we'll give time for one more question. Could you clarify what CAD formats or what PLM systems do you use?
Okay, that's going to be a big list. Right now for PLM systems, we've currently only completed our integration with PTC Windchill. There's been a lot of hunger for and request for, and we're working toward integrating with other PLM systems, but we haven't shipped that yet. As far as the CAD systems, for sure, we can bring stuff in from CATIA as a CATIA CAD assembly, but we could also bring in the 3D XML files that are a common interchange format from Dassault products within Dassault. So sometimes when people hand CATIA data off to SolidWorks, they'll use that 3D XML. We can import those 3D XML files too. From the Siemens world, we can bring in the NX files, so those are PRT and suffix, I think, as well as the JT files that are a common interchange format coming out of the Siemens world. We are also able to import PTC Creo, whether they're the Creo PVZ files or the Vuforia viewers PVZ, and I forget what the other suffix is. So we can bring in pretty much all those players. And if you're not talking about those major CAD players, we can still bring in a lot of those other interchange formats, such as 3D XML, FBX, JT files, and a list almost too long to run through. I've even brought in stuff from Google SketchUp before as either a STEP or an IGES in the past. So STEP files, IGES files, quite a few of the different formats of Parasolids, all of those come in. Even old school file formats like Vermal, those can absolutely come in.
Wonderful. Thank you. And that concludes our time for today. Thank you again, Eric and Meredith, for the informative webinar, and thank you attendees for joining us. See you next time. Bye for now.
Thank you very much. It was a pleasure.